Hello everyone. In this video we're going to talk more about covalent bonds and their characteristics and specifically covalent bond strength and covalent bond length. So I did show you a slide of showed the measurements of the bond length and bond strength. So let's talk about covalent bond strength, okay? How strong is that ionic or covalent bond? And it's basically, again, an electrostatic attraction, again, how strong is the covalent bond, or the strength of the covalent bond is influenced by the radii of the atoms, the polarity of the bond, and the number of electrons that the bond is sharing, okay? So what we're going to look at is a little bit of Zeph here too, okay? The effect of the atomic radii, I'm sorry, not Zeph, but the effect of the atomic radii. Smaller atoms result in smaller distances between charges, therefore there's a stronger attraction. So here we have an example of small atoms, okay? So again, this is, again, Coulombic force of attraction, or in other words, opposites attract, or in other words, lattice energy, or in other words, the inverse square law. The charges over the radius squared. So when we have a small radius, such as this one right here, we end up having a large force of attraction. So here is the atomic radii length, only 53 picometers, and notice the bond enthalpy. In other words, the energy it takes to break the bond, okay? Notice it's, how do I know it's energy to break the bond? Because it's a positive number. This is much bigger, okay? This is much bigger, the CL-Cl bond, and notice there's less energy. Why? Because the radius now increases, and anytime this denominator increases, the result, the lattice energy of the Coulombic force of attraction gets smaller. Okay, so we just do a little simple math there. Okay, so based off of that, the bond strength, here's another one. The effect of polarity, the more polar the bond, the stronger the force of attraction. So in this particular slide, let's go back one, notice we're dealing with the exact same thing. So this is one situation where they're exactly the same thing, HH and CL-Cl. But now what if we have two different things, perhaps a heterogeneous type of bond, okay? Now we have H being bonded with Cl and H being bonded with S. Now, Cl and S are right next to each other on the periodic table, so distance is not an issue here. Radius is not an issue, but the electronegativity value is. So when I look at the electronegativity value, Cl is farther to the right along the third period than S is. So therefore, it will have a greater electronegativity value. With the greater electronegativity value comes with a stronger attraction, and that results in a greater bond and a greater amount of energy it takes to break those bonds, okay? So notice I already mentioned this, the sizes are not constant in this comparison. However, the projected enthalpy of the HCl bond would be the average of the HH and the CL-Cl bond, okay? So you got to read into that just a little bit, okay? Now, strength. Notice strength also goes with the type of bond we have. So I'm not talking about just covalent bonds versus ionic bonds. I'm talking about a multiple bond type of thing, okay? So the effect of multiple shared pairs, now we only have a single bond here. We have a double bond here. And so therefore, with the shared pairs of electrons, single bond, double bond, now it takes just a little bit of energy to break a single bond. It takes a ton of energy to break a double bond. And guess what happened if you have something like a C-C bond with a triple bond? It's going to take even more energy there. Okay, so more bonds, more energy. Okay, now here's a couple questions for you. Here's this one. Whoops. There we go. A little tougher there. Here's this one. Let's get the whole picture here. Okay. Let's go back up. It's A, B, C, D. It's kind of hard to read. Oh, geez. Whatever. Okay, now length. Length has to do with size of the atom and also the amount of electrons that are being shared. So check this out. We have small atoms. H and H are the smallest atoms we have. Hardest to break, smallest length. So the closer they are, the harder it is to break. Seems to make sense. Spread them out a little bit. Cl is a little bit bigger than the H. Takes a little bit more, it takes a little less energy because they're farther apart. And there's the evidence of that. Now let's take a look at something a little bit different here. Now CC, Notice 347, 154 picometers. Check this out. Double bonds are shorter than single bonds. Double bonds are shorter than single bonds. There's the evidence of that. Okay, and we already looked at bond strength. Okay, a couple examples here. Okay, and we'll stop there. All right, if you have any questions, go ahead and email.